Okay, so today we are starting our notes for Chapter 7. How many of you have solved systems before? Systems of equations. All of your hands should be up. Yes, you probably solved them in Algebra 1, in Algebra 2, maybe some in geometry. We are shifting. We're going to spend the first part of the hour, most of the hour, reviewing the methods for solving, but we are going to look at some nonlinear systems today. Okay? So, quick overview. We're solving systems of two equations. Most of them will be linear, but not all. In section 2, we get into matrix algebra. How do we work with a matrix? That will be new to you from what I've heard. All right, you haven't done matrices before. We're going to look at row operations and how we use those to solve systems. In 7.4, we'll look at partial fraction decomposition, which is a really cool thing. And then in 7.5, we will look at some systems of inequalities instead of equalities. When I say cool thing, I do not mean hard. I mean cool, like awesome. You're going to love it. Trust me, Carter. You're going to love it. Okay. You've trusted me before, and it's backfired on you?
Very bad.
Well, we'll see when we get to 7.4. Okay. Today, we're just on 7.1. We're going to look at solving systems using 3 different methods. Substitution, graphing, and then what used to be called linear combination. I think in your algebra book, they called it linear combination. In our book, it's called elimination, but it's the same process. Okay? So you're not learning any new processes today, just reviewing them. Okay? So, the solution to a system of 2 equations and 2 variables is an ordered pair that is a solution to both equations. Right? We have solved the system when we have found all of the solutions. And I'm going to ask that you think about the shape of the graphs. Even though our main emphasis today is going to be solving algebraically, I do want you to think about graphically, what would this system look like? And am I getting the right number of solutions? Does it make sense? Okay. All right, so our first example, we are starting out with the substitution method. If we are going to solve by substitution, we have to have one equation solved for an x or a y. Okay, doesn't matter which. In this example, it's probably easiest to solve for that y right there. Okay, so can you picture adding y to the right-hand side and subtracting 10 back to the left? Okay, so we would have y equaling 2x minus 10. We okay with how I got that? All right, and now we're going to do a substitution. So I'm going to take my second equation, which was 3 times x plus 2 times whatever y is, and it has to equal 1. And I'm going to make a substitution, and in place of y, I'm going to plug in the 2x minus 10. Okay? And then we just have an algebraic equation to solve. 3x plus 4x minus 20 equals 1. That would be 7x equaling 21, and x would have to be a 3. Okay, so we're going to go through the solving part fairly quickly, just that algebra part. I'm assuming that's all review for you. What do we do now that we have x being 3? Yes, we're going to plug it back in, substitute it in. So y would be 2 times 3 minus 10, or negative 4. So my solution is the point 3, negative 4. Okay. Now, graphically, we have 2 lines here, right? The first one is in slope-intercept form. Means it starts down here at negative 10 and has a positive slope of 2. Where's it going to hit the x-axis? At 5. Right? I put a 5 in there, I get 0 for y. We said the slope was 2, so I can go down 2 and back 1 to get a few points on my line. Okay, now this second equation is not solved for y. We could do that. The other option for graphing that one, we can take this and look for the x and y intercepts. Okay? So if I put a 0 in for x, what do I get for y? All right, so 0, 1/2 is my y-intercept. If I put a 0 in for y, what do I get for x? 1/3. All right, so 1/3 is my x-intercept. And if we could draw the line through those, try to make yours nice and straight. Where do they intersect? At 3, -4? Okay. So the graphing part, for the most part, should be just a check. Okay? Is my answer reasonable? All right. Our second example. This one says we're solving a nonlinear system by substitution. Now, we gave you the graph, but we want to emphasize algebraically, how do we solve this? Okay? It says find the dimensions of a rectangular garden that has a perimeter of 100 feet and an area of 300 square feet. So we need perimeter and area formulas for a rectangle. What do we have for perimeter? Okay, so I'm going to say 2 lengths and 2 widths. Okay, and then how about area? Okay, so what we're told in our word problem is that 2 lengths plus 2 widths has to equal 100 feet, and length times width has to equal 300 square feet. Okay, now we're going to do a substitution. You have a couple options. You could take that area formula and you could solve for L or W. What that would create, though, is a fraction, right? If we solved the area equation for L, we'd have 300 divided by W, and we would be dumping that into the other equation. If you don't want to deal with the fractions, you can start with the perimeter formula and solve for L or W, right? It doesn't matter which. If I take 2L plus 2W equals 100, can I divide everything by 2? So L plus W has to be 50. If 2 L's and 2 W's equal 100, then 1 L and 1 W equals 50. Okay, so I can solve now for L or W, it wouldn't matter. Say I solve for L, I'm going to have 50 minus W. And now I'm going to plug that in. I'm going to substitute that in for the length right there. Okay, so I use the first equation to solve for a variable, and now I'm going to substitute it into the second equation. So now I have 50 minus W times W equaling 300. All right, let's go ahead and distribute. We have 50W minus W squared. If I move everything to the right-hand side, I have W squared minus 50W plus 300 equaling 0. Okay. Now, typically with a quadratic equation like that, we would try to factor it. Okay, this one is not factorable. What's our other option if it's not factorable? What? Quadratic formula. All right, so let's plug this into the quadratic formula. W equals, we need the opposite of B, so the opposite of negative 50 would be positive 50, plus or minus the square root. What goes underneath that? B squared minus 4AC. All right, so B squared, we have negative 50 squared. That'd be 2,500. Minus 4 times 1 times 300. All divided by 2A, 2 times 1. Okay? All right, so 50 squared is 2,500. 4 times 300 is 1,200. We have 50 plus or minus the square root of 2,500 minus 1,200, which would be 1,300, and divide it by 2. All right, so go through 50 plus the square root of 1300, and then divide by 2, and 50 minus the square root of 1300 divided by 2. There's calculators on my desk if you need one. You're going to get some decimal answers. Anybody got them yet? I heard 6.972 and 43.028. What do those add up to? They add up to 50. What happens if I put 6.972 back in here? 50 minus 6.972 equals the other answer, right? The 43. So my width would be about 7 feet, and my length is going to be about 43 feet. Okay? You're getting both answers because it doesn't really matter which one's length and which one's width, right? A times B is the same as B times A. So works out the same. So our rectangle is about, what do we say, 7 feet by 43 feet, rounded. Okay. Questions on that one at all? Okay, so when you are dealing with decimal answers, you should not be rounding anything until the very end. Okay, if you start rounding them in step 1 and you round again in step 2 and you round again in step 3, pretty soon your answer's far off from what it should be. Okay, so make sure you keep those, you've got calculators, keep your decimals in the calculator till the very end. All right, shifting to a non-linear system. We can still solve by substitution. Our system here says y equals x cubed minus 6x. X cubed, remember, is that twist shape, okay, which is the blue curve in our picture here. And then y equals 3x is just a nice linear equation going through the origin, slope of 3. Okay. I want you to take a look before we start at the scale that you're given here, the window. We are told we're going from -5 to 5 for our x's, and we're going from -15 to 15 for our y's. So think about the tick marks. In the horizontal direction, the tick marks are just going by 1s, but in the vertical direction, they're going by 5s, right? If we have to go from 0 to 15 with 3 tick marks, each one is 5 units. Okay. How many places do we intersect in this picture? So we should be getting how many answers? 3. Okay? We're going to solve this, like I said, using substitution. If y equals x cubed minus 6x and y equals 3x, we can substitute this in here. So now we have 3x equals x cubed minus 6x. All right, let's get everything to one side. That would give us x cubed minus 9x equaling 0. And then what could we do? Good, we could factor an x out. That leaves me x squared minus 9 is the other factor. Can we factor that again? What do we get? Okay, so solutions for x. X could be 0, x could be -3, and x could be +3. Okay, what do we get for the y coordinate? It should not matter which equation you plug them into, right? You should get the same answer either way. So let's use the easier one, the bottom equation, y equals 3x. So 3 times 0 would be 0. 3 times -3, and 3 times +3. So we're getting 3 ordered pairs. The first one is 0, 0. The second one is the point -3, -9. And the third one is the point 39. Now look at your graph. Do those answers look reasonable? Okay, here's our 0, 0. We have the point 39 over 3 up 9. And we have -3, -9. Okay. Yes? All right. So again, make sure your emphasis should be on, can you solve them algebraically? Okay. How are we doing with substitution? You feel pretty comfortable with that? Okay. We are going to look at a couple graphically because they are harder to solve algebraically. We have one of our equations be a natural log equation. I want you to talk at your tables before you grab your calculators. What does y equals the natural log of x? What would the graph look like? And what would the graph for y equals x squared minus 4x plus 2 look like? What's the basic shape? Okay, so what did we come up with for natural log? What shape is it? Yes, good, Max. All right, natural log, it's going to come up along the y-axis and curve off to the right. Remember that shape? Okay, what is the other one going to look like? It's a parabola. Does it open up or down? Opens up. What's the y-intercept for that parabola? If we put zeros in for x, we get 2 for y. Okay, so it's going to intersect up here at 0, 2. All right, and it's going to open up. So it's going to come down like this somehow. Yes? We could find the vertex and stuff, but we're going to let our calculator come up with our solution because it's not a nice integer value. So grab your calculators, put this one in as y1 and this is y2, and do an intersection. You can split it up at your tables. There's 2 points that you should be finding, so each of you find a different one. All right, who's got one of them? Yes. Okay, thank you. And the other one? Somebody else? 3 point. Can you give me 3 decimals? It only went. Okay. And the other one? 1.34? Okay. Agree? All right. Now, question 3 says, use your knowledge about the graphs of logarithmic and quadratic functions to explain why the system has exactly 2 solutions. They gave us a viewing window here so that we could make sure and see the critical pieces. If they hadn't, would we have known how many solutions to look for? For example, what if I had set my window and I was only seeing that much? Would I know that there's another one out there based on the shapes of the graphs? Yes, we know what a parabola looks like, right? We know that our arrows are going to continue in that direction forever, but we also know this log graph is curving off to the right. So we know that there should be some other point out there. Okay? So make sure that you're keeping in mind the shape of the graphs when you look at the calculator And maybe you have to make your window bigger, all right? If you're solving the system, you want to make sure you find all intersection points. Are we confident that there aren't any more than the 2 we found? Yes, because our parabola is opening up. It's not going to come back and swing back down and hit again, right? Our log curve is curving off to the right. It's not going to twist and somehow meet up with that parabola again, okay? All right, example 3. Go ahead and do this on your calculators. You should know the shape of both graphs. What is the 2 in front of that natural log going to do to my previous graph? It's going to stretch vertically, okay? What's an x squared minus 1 going to look like? Parabola is shifted down 1? All right, go ahead and graph it and find the intersection. Anybody got it? All right, I heard someone say 1, 0. Agree, disagree? It intersects just in that one spot. Did anybody get something other than 0 for a y coordinate? Okay, so negative 2.1 times 10 to the negative 12. What does that mean? A really, really, really tiny number, right? You're going to have a decimal. You're going to have 11 zeros before the 2. Okay, so very, very, very tiny number, basically 0. Yes? Sometimes your calculators will round it for you. Sometimes they go out to this unreasonably tiny, tiny number. All right. So that's what you're going to be doing for tonight's homework, but we are going to continue the notes so that tomorrow when you're doing your ACT, you don't have a video to watch. Okay? So that method of elimination, we said it's the same thing as linear combination. Okay? So to solve by elimination, our goal is to get our 2 equations so that we have opposite coefficients for one of the variables. All right? For example, if we had a 2x and a negative 2x, all right, when we add those together, the x's would drop out. All right? That's the goal. So in example 4, we are going to need to multiply both equations regardless of whether we eliminate x or y. Sometimes you can get by with just doing one. In this case, it really doesn't matter. So pick one, x or y. What do you want? X. We're going to eliminate x. All right, so what do we have to multiply the first equation by? Okay, so if we multiply by a 3, we've made that into a 6x. That means in the next equation, we need a negative 6x. So we're going to multiply by a 2. All right, so take a minute, multiply those equations by their respective numbers. And when we add them together, what happens? Good, the x's cancel out. We end up with 19y equaling 57. So y would have to be 3. All right, then how do we find x? Plug it in. All right, does it matter which equation we plug it into? No. All right, let's say we plug it into the top one. All right, so we have 2 times x plus 3 times 3 would be 9. And solving that, 2x would have to be negative 4, so x would have to be negative 2. So my solution to the system is the ordered pair negative 2, 3. Okay. We won't take time to graph that. Now, in all the systems that we've done so far today, we've been able to find at least one solution, sometimes 2 or 3. There are times where you will get no solution. If we're talking about linear equations, what kind of lines would we have that create no solution? Parallel lines. Now, most of the time, you're not given equations in slope-intercept form where you can tell you have parallel lines, all right? And it's not going to say, hey, this one has no solution, right? So, assuming we didn't know that, I want you to look algebraically at what would happen as you're solving it that leads you to that no solution answer. So, using elimination again, let's say we're going to eliminate the x's. What would we multiply this top equation by? Right. So multiplying a -2 in there gives us -2x plus 6y equaling 4. I'm going to bring down my second equation. I didn't have to change that at all. And what happens when I add these together? The left side is gone, right? The x's and the y's both cancel each other out. But what do I have on the right side? I have 8. Can 0 equal 8? No. When you get a false statement like this, where there's no variables left and what you do have left doesn't make sense, that's your no solution. Okay? Yes? Okay. Could we also solve those, get them in slope-intercept form and show that we have parallel lines, different intercepts? Okay. But again, you're not going to know to do that. So this is a better route. All right, so graphing lines. We have 3 things that can happen. The 2 lines can intersect in a single point, which means we get one solution. We could have 2 lines that are parallel, like in our last example, where we get no solution. What's the third case? Infinitely many solutions, right? This is the case where we have 2 lines that are actually the same, 2 equations that are the same line. All right, we say the lines coincide and we get infinitely many solutions. So let's look at one example, quick review that. What are we going to multiply the top equation by if we want the x's to drop out? All right, times it by a 3. That gives me 12x minus 15y equaling 6. And what's different about this one compared to the last one? What? Yeah, everything drops out on both sides. And we have a true statement. 0 does equal 0. All right? When you end up with a true statement, that's where you have infinitely many solutions. But I'm going to ask you to write one extra thing this year. In the past, all you had to do is say infinitely many. Okay? We're going to say infinitely many solutions such that, and then you're going to give me one of the equations. I don't care which one you use. I'll use the top one, such that 4x minus 5y has to equal 2. And what we mean by that is you can't just make up an ordered pair and say it's going to work because there's an infinite number of solutions. What we're saying is all of the solutions to the first equation are also solutions to the second equation. Okay? But your answer has to work in the equation. Does that make sense? I can't just put 2 numbers together as an ordered pair and say, here's one of my infinite number of solutions. Okay? But if I have an ordered pair that works here, in this one, I know that it'll work in the other one as well. Make sense? Okay. The last thing we are going to do is a couple application questions. You are going to need graphing calculators for this, so grab yours. If you don't have one, grab one off my desk. And what I want you to do first of all is go under Stat and Edit. And if you have data in there from previous examples, I want you to clear it out. Okay, so remember how we do that. We go up to where it says L1, L2, L3. We hit the clear button and then arrow back down and it's gone. Okay, so just clear out everything. And then also go into your y equals screen and make sure you've cleared out any of your old equations that we've had from past examples. Okay, we want a blank slate. All right, so what we're going to do, so we're going to enter 3 lists of numbers. But for this example, we are going to say that x being 0 represents the year 2000. So when I look at my year list, okay, I'm going to put this in list 1. But I don't have to enter 2001. I just have to enter 1. Okay, so my list 1 is going to be the numbers 1 through 7. All right, go ahead and enter that. And then in list 2, I want you to put the dentist information, and in list 3, the health insurance information. All right, let's pause the video here for a sec while you guys do that. Okay, so we've entered the year as 1, 2, 3, 4, 5, 6, 7 in list 1. We've entered the dentist information in list 2 and the health insurance in list 3. Okay, first thing I want you to do is get a scatter plot of the data. So we are going to go under Stat Plot. Okay, and we're going to use plot 1. Okay, so second y equals. Plot 1, make sure you turn it on and that you select the scatter plot icon and that your x's are coming from list 1 and your y's are coming from list 2. And for this first one, go ahead and use the little square symbol. Those of you with the color one, pick a color for this one, and then the second one will do a different color. Okay. Now go back to Stat Plot, go to Plot 2, turn it on, select Scatter Plot, and this time notice we want x's from list 1 but y's from list 3. And then choose a different symbol, like the plus sign, so that you can tell the two apart. Okay? Now, what kind of window should we set? Well, our years are going from 1 to 7, so they've made it a little bit bigger. All right? We're going to use that for our window. Where x's are going to go from -5 to 10. And then if you look at the data, our y values, the highest one was 153.2. So we're going to go from like -25 to 200. Okay? So set your window and then graph it. And you should see 2 different scatter plots, one with little squares, one with little pluses. I'm going to go from -5 to 10 by ones, and then from -25 to 200. You can just do 0 for your 2. X min, X max, Y min, Y max. Okay, everybody got it? Their picture? All right, we're going to go now and do a linear regression for each of those. Okay, so we're actually going to go through and do 2 different equations. So the first one, go back to Stat and Calc. Okay, Stat Calc, and this time we're going to use number 4, linear regression. Okay, where yours says X list, Y list, okay, Remember, we're using list 1 and list 2 for the first one, and I want you to store it in Y1. Okay? To store it, you go under Variables, over to Y Variables, Function, and then select Y1. Okay? I know your screen's going to look different than mine. Mine's an older calculator. Okay? Hit Enter, and it should give you your equation. All right, notice your R value is almost 1.99644. All right, very good fit. Okay, now let's go back and calculate the second one. Okay, so go back to Stat, Calc, Linear Regression. This time we're using list 1 and list 3. And we want to store this one in Y2. Okay, so variables, Y variables, function, but this time select Y2. All right. Okay, now when you hit graph, those two lines were dumped into your y equals screen, so it's now going to graph those lines on top of your scatter plot. Do they intersect? Yes. And here's why they had you set the window back a little further than we might have pictured doing, because they intersect prior to the data that we were given, right? They're intersecting back here. Okay, so go ahead and do an intersection. Find where those intersect. So second trace, number 5, intersect. Enter, enter, enter. You need to put a comma in between those. Okay, then comma, and go variables, y variables, function, and then put it number 2.
Okay.
Okay, so where do they intersect? Negative 2.572. All right. Well, what does it mean to have them intersect at time negative 2.5? Right. So if we started at year 2000, right? Time 0 was 2000. We're going back 2.5 years. So we're back into 1997, about halfway through 1997. Okay. And how much did each one, what was the personal consumption expenditures where they were the same? 49. What unit would you put on that? 49. Look at your chart. Your numbers are in billions. So they are going to have $49 billion for both dentists and health insurance. Okay? Questions about that one? All right, we have one more to look at. Have we done anything new today? I think you guys have done it all in past classes, right? We're just doing a review. Maybe not so much with the nonlinear systems, okay? But substitution, graphing, and elimination, or linear combination, all of that should be a review. Okay. You've heard the term supply and demand? All right. It says, suppliers, will increase production X if they can get a higher price P for their products. All right? So both variables increase together. As X increases, Y increases. All right? As the amount you make increases, the price is also going up. Okay? So that's the blue curve. Consumers' demand for a product will decrease as the price goes up. Okay? If people charge too much for things, you're just not going to buy it. Okay? So we have a blue supply curve here. As X gets bigger, Y is also increasing. Our demand curve, though, as X increases, Y is going down. The more something is available, the less people want it. Does that make sense? Okay? You can flood the market and then they don't care. The price is going to go down. You can't sell it all. So what we want to find is what's called the equilibrium point, where those two meet. What production levels should we shoot for where what we're supplying and what the demand for it is match? Because we don't want to make a whole bunch of a product and then just have it sit on a shelf. Okay? Now, where they meet, that's going to tell us how much to make, but it's also going to give us what we call the equilibrium price. What should we sell it at so that we can sell it all? All right? Everything we make will get sold. All right, so our example here. We have a manufacturing company that has determined the production and price of a new tennis shoe should be geared towards the equilibrium point for the system of equations where the demand curve, or line in this case, is 160 minus 5x equaling the price. And for supply, we have price equaling 35 plus 20x. It says the price P is in dollars, and the number of shoes X is in millions of pairs. Okay? Find the equilibrium point. So where are these two going to intersect? All right, we can go ahead and use substitution. If P equals 160 minus 5x, we can just substitute that for P in the second equation. All right, we're basically saying 160 minus 5x has to balance with 35 plus 20x. All right, combining our x's, we'll get 25 on the right-hand side, subtracting 35. Okay, and what's 125 divided by 25? 5. So what does that mean? If x is 5, what did they say x stood for? Millions of pairs of shoes, right? So we're going to make 5 million pairs of shoes. And now we just need to figure out what price are we going to sell them at. Okay, so putting a 5 back into our equation, our price is 160 minus 5 times 5. 160 minus 25 would be 135. Okay, so if we make 5 million pairs of these tennis shoes and sell them for $135 each, we can sell it all. Okay, that's insane. Okay. So I'm going to give you both assignments. The first one is what you should work on tonight. Most of it is substitution with a little graphing. The second one deals more with the elimination method and a few applications. Feel free to take a picture of that since we're short on time. Okay, so when you guys come back on Thursday, since you'll be gone for the ACT tomorrow, when you come back on Thursday, you should have both of these done.
Can you have them on the same page?
You can put it all together, yes.